Hello and welcome to NCC Group's Cryptopals guided tour. My name is Eli, I'll be your guide. In this video, we're going to be looking at challenge 3 from set 1. This is one of the more entertaining challenges in the first set in my opinion. This involves single-byte XOR. We have a hex-encoded string here that has actually been encrypted, so we essentially have to find the key and decrypt the message. This is trivial to do by brute force because there are only 256 possible values for the key, so we could just print them all out and then scroll through the list and look for the one that looks right. But we're going to automate the process. The way that's going to work is through frequency analysis, which is a classic technique from classic cryptanalysis. Works great on all sorts of traditional ciphers and on this slightly more modern iteration on the traditional cipher. So we are going to evaluate character frequency on our candidate plaintexts and then take the one that looks most plausible. First off, though, we need to know the expected frequencies of different characters in English. We could download some list from the internet that'll tell us what the canonical frequencies are, but I'd actually rather generate something from scratch. And so let's just do that. I like Frankenstein, we'll go with that. And we will save this as frankenstein.txt. This work, of course, I believe is comfortably in the public domain and free for us to use. So let's go ahead and use it. Now this is a fairly long string containing the contents of the book. And we are going to count character frequencies in it. We're going to collect a few different counts here because I want to show you some interesting things that happen when you try to solve this challenge different ways. All three of these strings are exactly what you would expect them to be. Let's go ahead and count ASCII lowercase first. Actually, let's define a function that's going to do this for us because we're going to be counting all three of these in very similar ways. This right here gives us the sum of all the characters counted in the text, which is not necessarily going to be equal to the length of the text because the letters that we're counting are not all of the characters that appear. There's also going to be punctuation, white space, symbols, and if we're only counting lowercase letters, then obviously uppercase ones wouldn't be counted, etc. So we just take the sum of all the letters we have counted, and then we're going to divide each individual count by that to get the frequencies for each individual character. We're going to use a dictionary comprehension to do this, which is the sort of thing that's good to know how to write because it'll clean up a lot of your Python code. There you go. And so this just sets a key and a value for every entry in letters. So here are the lowercase frequencies. And if we count uppercase characters, we see some interesting stuff. Z does not appear at all in uppercase, for example. X is exceedingly rare. There's a couple other fun things to note there. That actually E, the most common lowercase letter by a wide margin, is not even close to being the most common uppercase character. And then if we want to create a combined count of lowercase and uppercase, here's that as well. Now intuitively, you might think that this is the best one to use. It's the first one we'll try, and we'll see how it works out. So let's copy that. Oh, and we can remove this text file now that we don't need it anymore. And we will use the excellent black tool for formatting these. Black is a Python library that's also available as a Vim plugin. It's a reference to the Model T. It comes in any color as long as it's black, and works super well for formatting into a subset of PEP8 that is generally pretty good. I have a couple minor quibbles with it. Sometimes it messes up line lengths, and sometimes I like to go rogue and do things that it wouldn't condone, but in a lot of cases it's super useful for just stuff like this. So now then, let's get to work. Given a plain text, we're going to want to compare the character frequencies in it to the character frequencies here. So let's define a ScoredText function that will do exactly that. And you'll notice that there's a little bit of confusion between strings and bytes here. The text of the book is a string by default, and we've generated individual characters here. I think that's more readable than if these had, ordinal values for each byte. But our plain texts are obviously going to be bytes because we're going to get them from XOR. And so we're going to need to be conscious of string to byte conversions. And the way that I'm writing this is the way that, in my opinion, involves the minimal hassle, but it is still a non-zero amount of hassle. And this is exactly the sort of thing that the Cryptopals rule from Challenge 1 was trying to warn us about. So we're just going to take the difference between each frequency and the expected value for it. We could also take squared differences, but I think that it's not really necessary to get that fancy here. So let's go ahead and do this. And we're using OR here to convert from strings to byte codes, right, to an integer representing an individual byte. And we're dividing here by the length of the text, which is not strictly correct, but it simplifies the code a little bit, and it's close enough for our purposes. And actually, spoiler alert, we're not going to end up using this function in the final version of the code. This is just an intermediate little thing to show you the simple way of solving this problem before we get to the optimized way. So minor little issues like this don't matter a ton. Anyway, our score is going to be a cumulative sum of the differences between each expected and actual observed frequency in the text. And so higher scores naturally are worse. Lower scores are better. And let's go ahead and note that here. There we go. And now that we have this, we are actually prepared to try to solve this problem, or to take our first crack at solving it at least. What do we want this to return? We could return a key. We could return a plain text. We'll return plain text for now. We're going to rework this later. We could return a tuple, actually. This will be a tuple with a key and a plain text both. We're going to iterate over all 256 possible values for the key, and for each one, we're going to compare it to the current best score we've found, and we're going to update this variable based on that comparison so that it ends up having the best scoring ciphertext along with the corresponding score, or excuse me, the best scoring plaintext. And so in order to ensure that at least one of those values is used, we're going to start the score out on infinity. This is one really convenient thing about using floats, is that they actually do have a representation for infinity that you can use like so. So this basically guarantees that our first iteration through the loop will result in updating best guess, and that it will therefore have some initialized value or other. We're going to take our single byte key, expand that out to the length of the ciphertext so that we can XOR the two of them together, and then recover the plain text through that XOR. But we actually need to import our XOR function to do that. From challenge 02, import bytes XOR. Now we don't know if this is the correct plain text or not, but we'll generate a score on it regardless, and then we're going to pack these into a tuple. Now, tuple comparison works element-wise, so it will compare the first element of each entry in the tuple, and then if they are equal, then it will compare the next element as a tiebreaker. With floats, they are almost never going to be equal, so we can use this to compare a combination of a ciphertext and a score in a clean way. And we're using min to do that. This will just take whichever between the best guess and the current guess has the smaller score, which on our first time through the loop is obviously going to be the current guess because it's comparing against infinity. And from then on, it'll update based on whichever text looks better. So by the end of this loop, it'll have the best out of all 256 possible guesses, and it'll return that. Well, actually, rather than telling it to just ignore that, let's add a check here. Oh yeah, and I suppose we are actually putting a score in here and not a key, so it doesn't make a lot of sense to return the score. So let's just return bytes for now. And there we go, that makes our linter happy, and it will work just fine for our purposes. Now, another thing we could do that would be cool would be if we wanted to view, for example, the, say, top 5 possible results. We would not be able to do that with this function as it's written, but we can write a worse version of it that gives us more information. So here's a version that will return the top 5 candidate plaintexts, which will actually allow us to see not only what's the most likely one, but what sorts of results are we guessing here. So this will give us more visibility into the technique that we're using, and I'm going to use that for now. Now let's get started here. I'm going to take our ciphertext string, This, by the way, is a pretty printer that will allow us to display these results in a way that's easy to read. There we go. So here's our top 5 possible results. And we can see that the top result is not exactly correct. It's close. This second place result is clearly the right one, but that one did not win out for whatever reason. There's a couple possibilities for why this might be. One thing you'll notice is that a lot of these have ASCII characters in the same indices as one another, and then non-ASCII characters in the same indices as well. You might be wondering why that is. There actually is a reason for that. Let's take a quick detour to look at why that is. If we look at the ASCII table here, you'll notice it's actually laid out so for example, this is the hex table on the left here, and this is the high hex digit, this is the low hex digit. So for example, 31 is the number 1, 32 is number 2, 41 is A, 42 is B, etc. And so what you see here essentially is that there are certain bits that you could flip that would scramble the ASCII character that you're getting, but would make sure it is still a letter. And this is on purpose. This is by design. It's actually kind of a cool idea. Because for example, between 4 and 6, to flip from 4 to 6, you literally just XOR a 2 into that. Or actually in this case, I guess it would be a 20. So you XOR OX20 against this, and you can flip the case of your string, for example, which back in the day actually kind of mattered. It's a useful thing to be able to do performantly. These days, we are not coding under the same restraints that people used to be under. We're not constrained in the same ways, at least not usually. And so a lot of stuff like this we no longer need to know, but it is still kind of cool to see. I think it's interesting. So anyway, our first result is not correct. And the reason for that, I'm just going to go out on a limb and say I am blaming the fact that we are using this whole frequency count set here. I think that there are too many infrequent characters that are throwing off the overall result, and it would be better to use a smaller set of the most common characters. So let's actually, no, before we end up doing that, we're going to take one other detour here because I just want to show you what happens. Just indulge me here. So let's try doing separate scores for lowercase and uppercase. Because if we're saying that, okay, the problem is actually combining these all into one dictionary, what if we do 2 dictionaries? What happens then? And let's see. Something like this should be just fine. And now we are going to run the function again. We don't really need to change anything else. We're just changing how we're scoring things. And now this is significantly worse. I don't recall if this is actually the same result as before, but it certainly seems like it could be. So that's a no-go as well. That's definitely a no-go. But what if we only count lowercase? Lowercase characters are by far the most common characters in almost any plain text, and so it's where we might expect to get the cleanest frequency counts. And by cleanest, I mean largest sample size and least number of expected outliers, both of which are super important here. And there we go. Like I said, least noise, best score, and it gets us the correct plain text. So we've solved the challenge, but I don't know about you, but I don't really feel all that good about how we've solved it. I think there's a lot that we could do to clean this up. First, let's add that name guard. We've put that off for too long. We'll switch over to the normal crack XOR cipher function. And let's confirm that that one works as well. There it does. So a few things we could do to improve this. First off, let's not be shuffling tuples around. We can use a data class to encapsulate these values and allow us to reference them by name and basically just make this code a lot cleaner and more readable. So let's do that right now. This is something that started as a third-party library, and then a large subset of that library was implemented in standard lib. I really, really, really like this. I think it is conducive to a lot of good coding patterns, and it's just super convenient. So I'll show you how this works. And we're going to import both the data class decorator and this other function that I know that we're going to need down the road. So we're going to define a class called ScoredGuess, and this is going to encapsulate all the information related to a guess that we might be making about the value of the key in plaintext. And all of the fields are going to be optional, so we're going to need that as well. So in order to mark this as a data class, we put the data class decorator on it, and what this allows us to do, I really recommend reading the man page for these, or excuse me, not the man page, the Python docs for these, because it is super, super useful. So the way that a data class works basically is it allows you to specify a number of attributes, and then it will automatically build a constructor that takes all of those attributes as arguments. So for example, I can say score is a float that defaults to infinity, and then key is optional. If it exists, it'll be an int, and it defaults to none. And to be clear, this use this key. To be clear, I just add the comment here because usually a key is going to be bytes, not int. So it's just a little reminder that we're doing repeated key XOR with a single byte key. So if we happen to have computed the ciphertext and or plaintext, then we can include those in here as well, and they'll be rolled in with the rest of these values. And by default, these can't be compared to one another the way that tuples can, but we can add, or maybe it's just order. I think it's just order is true. Yeah, there we go. We can add this, and now this will automatically generate what are called dunder methods. Dunder for double underscore, meaning it'll be things like for less than, or this for greater than, which allow you to do native comparisons on these things. And so providing order equals true means that the data class decorator will automatically construct these for us. And that means that we can pass ScoredGuess instances into min, and it will give us the one with the lower score. If the scores are equal, it'll move on to comparing the keys, from there to the ciphertext and plaintext, but it'll never get that far because the scores are all floats and they're all going to be different in all likelihood. So there we go. This is our little data class, and let's actually do something a little cool here. We'll give it a class method. That allows you to pass in a key, and it'll auto-populate everything else. A key and a ciphertext, I guess you need. And this will just work exactly how we have our other logic working below. This just encapsulates this complexity. And this constructor is automatically populated by the dataclass decorator, so we don't have to declare that. And we now have a super convenient way of creating scored guesses from a combination of a ciphertext and a conjectured key. So let's go ahead and rewrite crack XOR cipher to use that. And this is going to clean this up a whole heck of a lot. And the plaintext is what we really care about, so let's make sure that that's not none as well. And there we go. I think that reads a lot better, personally. And we'll add a little note in here, in case it's not obvious why min is applicable here. And all right, this should work nicely for us. Oh, and let's clean up our actual reporting here. So instead of pretty printing now, we can go ahead and... This, by the way, is an example of something that Black does that I don't like. If the line is too long, it'll break the argument out onto its own line, which makes sense, but personally I think it reads better like this. I mean, if you saw, for example, this, I mean, you know what the rest of this line's going to be, right? Like, it's just going to be hex characters. So I don't think there's really any need to break that out, but I don't know. Matter of style. And in any case, it's easy enough to undo. And when you want to get the values out of a data class really tersely, you can get them by name. You have to do this for all four, but personally, I'd prefer to only have to write their names once and keep it all in one line, and this allows you to do that. You just have to make sure that this side of things is specified in the same order as the values are declared up here. And now, we can just report the key in the plaintext. And note how easy it is to keep both of those associated, by the way. No need to worry about type signatures or, tuple ordering, any of that crap. And there we go. We have the key, we have the plaintext, and the plaintext works just fine. Or the plaintext looks just fine. Our crack script works. Frankly, this looks good to me, but there is one further optimization that we can do based on the nature of the cipher that's in play here. So what's important to understand about this cipher is that it's what's called a substitution cipher, which means essentially that it performs a set of substitutions on the input. In this case, they're per byte substitutions. For every given byte, it has a different byte that it will replace the plaintext byte with. But if it encounters the same byte in multiple places in the plaintext, it will perform the same substitution each time. So essentially, the frequency counts that you will observe for different bytes in the ciphertext will be a permutation of the frequency counts of bytes that you will observe in the plaintext. And this permutation is defined by the key that we're encrypting or decrypting under. And so if you know the key, you know the permutation. What this means is that we actually only need to count frequencies once when we're cracking this cipher. And this is an optimization that was pointed out to me by my colleague Marie Sarah, which I really appreciate because it allows us to speed up the core loop by a lot. And this would matter a lot more if we had a longer ciphertext, but you'll see that even with a short one like this, it is a noticeable improvement. So let's write an optimized version of this cracking script that's going to take advantage of the fact that this is a permutation cipher. Or excuse me, as a substitution cipher, meaning that it maps the input space to a permutation of itself. And this loops over every byte, and for every single one of them, counts how often it appears in the ciphertext divides that by the ciphertext length, and so this gives us accurate frequency counts for every byte. Notice that this is not constrained to any given character set. This is every single byte. I just want to point that out because that's a difference from what we've been doing earlier. We're going to use the same error metric as before. This fucking autocomplete, God, that's annoying. And this is where the permutation comes into play. We know that the frequency count for the quote-unquote decrypted value of this ciphertext character is going to be equal to the frequency count of the original ciphertext character XOR the key. So this is where we're doing our permuting. And this allows us to get the score for the frequency count of this decrypted character without actually generating the decryption or counting characters within it, which is kind of cool. And is the core of the speedup here. And it's a non-negligible speedup because we're running this loop 256 times. So any tiny speedup that happens inside it is going to be magnified 256-fold. Oh, and I have made a slight mistake here by having those names be inconsistent. So let me just fix that. And we don't need to populate these values within the tight loop here, so we don't. But once we have our best guess, we might as well populate them before returning. So there we go. And as we can see, this works just as well. And just for fun, let's go ahead and benchmark both of these solutions. And by the way, what I'm doing here, the -i flag takes this script, runs it, and then fires up an interactive prompt after it has been completed so that you can interactively work with the names that are defined inside the script. This is available in the standard Python interpreter and also in IPython. This is super useful, especially for, debugging work in progress. So let's see how long this takes on average. 3.24 milliseconds. And this one, oh man, that's good. Yeah, so you can really see the difference that this optimization makes. So that's really cool. And I'm actually going to go back and rename these. This is going to be the canonical way of doing this. And there's going to be a couple other problems where we have to crack XOR ciphers. So it's good to have a fast, performant way of doing that. So we're going to make this the canonical one, and this is going to be kept around because it's simpler. We're just going to call it crack XOR cipher simple. So this is just illustrative, for educational purposes, and this is for getting work done purposes. Right on. So that's pretty cool in my opinion. I'm really happy with how this one turned out. Thanks for watching. Hope you learned something, and I hope you'll join me for the next one.